In today's lesson, we're going to be looking at solids of known cross sections. So for example, let's say we have a region in quadrant 1. So there's my first function, there's my second function, and this is my region R right here. But this time, we're not going to be revolving this region anywhere. We're going to state that sections perpendicular to the x-axis, sections perpendicular to the x-axis are the base of a square. So what you have to imagine is that's the base of a square, and there's a square coming up out of the screen of the computer. Now it's kind of hard to visualize, so I'm going to refer to Khan Academy for 1 second, and I'll show you the diagram of what this looks like. Just going to speed this up a little bit. So there's the region in 3 dimensions. Okay, so that should kind of give you a visual, sorry I moved it back too far, of what the object is looking like. Now, sometimes the base might be the base of a semicircle, so you'd have to imagine semicircles coming out of here. Sometimes it might be a rectangle whose height is 4 times the length of the base, so you have to imagine a rectangle coming out that's higher than the base. So the key to the question is they'll always tell you cross sections perpendicular to the x-axis or the y-axis, and that's where you're going to draw your slice. Okay? Well, let's say, for example, let's go with 2 equations we know. Let's say that this is y equals root x, and this is y equals x squared. We already know that the intersection points are 0 and 1 because we've used these 2 functions many times. And let's say that the cross sections perpendicular to the x-axis are forming a square. So what I need to do is I'm going to define the volume of this object. I'm going to integrate from 0 to 1. And all I'm going to do is I'm going to put in the area of whatever the shape is for my integrand. In this particular case, the area is a square. So this line is the base of a square, and the area of a square is side length squared. So it's going to be the integral from 0 to 1 of whatever the side length is squared. And to figure out the side length, it's simply the top of that slice minus the bottom of that slice. So it's going to be the integral from 0 to 1 of the top of the slice, which is root x, minus the bottom of the slice, which is x squared. So that's the side length. And since it's a square, to find the area, you must square the side length, and that would be the integrand. So now, again, all we're going to do is we're going to get out our calculator, and we're going to calculate this. So this is the integral again going from 0 to 1. And I'll open up my bracket. And again, my equation was root x minus x squared. Whoops, I got to back up there for a second. I have to get outside the root function. Root x minus x squared. and this whole thing is squared with respect to x, and that is going to equal 9 over 70. So therefore, the volume of my three-dimensional shape would be equal to 9 over 70. Now, we're going to use the same picture in the same diagram, but we're just going to change the shape. Let's say the question says that this is the base of a rectangle whose height is 3 times the length of the base. So to find the volume of this object, again, I'd be going from 0 to 1, and the area of a rectangle is base times the height, and my base is this line right here, so that would be root x minus x squared, and it would have to say in the question something to the effect that the height is 3 times the length of the base. So the height is going to be 3 times the length of the base. So therefore, if I multiply these two things together, it would be root x minus x squared all squared. So my integrand would be 0 to 1 of 3 times root x minus x squared all squared dx, and you would integrate that to get your volume. So the only thing that's going to change is the integrand, and the integrand is going to reflect the area of whatever three-dimensional, or of the area of one slice of this three-dimensional object that we're trying to build. So let's take a look at this example here. So we have the base of a solid, and this time we're just in quadrant 1 of the function 4 minus x squared. So that would cross the x-axis there, and that would be there. And it says, there's my equation, 4 minus x squared. And it said slices perpendicular to the x-axis are squares. So again, you have to imagine that a square is coming out the same height as the length of that line. So to find the volume of this shape, we're going to be integrating from 0 to 2. And then we are going to look at the side length all squared, because that's how you find the area of a square. So the integral is from 0 to 2. The side length is just the area under this curve. So the side length is defined by the function 4 minus x squared, and I must square that to find the area of that slice, and there is my integral. So now to find the volume, I have to do the integrand, and this time we said we're going from 0 to 2, and my integral was 4 minus x squared all squared dx, and that works out to be 256 over 15. So this would be 256 over 15. All right, let's do this exact same question, but now we are going to say that the base is the base of a semicircle. So again, here's my function 4 minus x squared. It crosses the x-axis at 2. It's just in the first quadrant. So now you have to imagine that this is the base, and I have a semicircle coming out of this base. So what we need to do is we need to find the area of a semicircle. And we know that the area of a semicircle is equal to pi r squared over 2. So to figure out the volume of this region, again, I'm going to integrate from 0 to 2, whatever the area of my semicircle is. And the formula for the area of a semicircle is pi r squared over 2. Now, you have to be careful with this because the total length of this slice is the diameter. So the radius of this semicircle is going to be this length, which is defined by the function 4 minus x squared, and that's all divided by 2. So that's going to be my radius. So to make my life easier, I'm going to bring the pi over 2 out front because it's a constant. And now it's just the radius, which is 4 minus x squared over 2 all squared dx. You could simplify this a little bit. This would be pi over 2. Squaring the top is just 4 minus x squared all squared. Squaring the bottom is 4. And if you want, you can bring this 4 out front and times it by the pi over 2 to get pi over 8. The integral from 0 to 2 of 4 minus x squared all squared dx, and that would be your integral. And now we just punch this into our calculator. So I'm just going to clear this, clear some of this stuff out of here. And we want the definite integral. Again, we're going from 0 to 2. And it was, in brackets, 4 minus x squared all squared. This is all squared with respect to x. And if we work that out, it's 256 again over 15. But now I have to times that by pi over 8. And my answer works out to be 32 pi over 15. So that would be my final answer, 32 pi over 15. So the only thing that really changes is going to be this integrand right here, and it's all based on what the area of one of those slices is. Okay, so if we're integrating with respect to the x-axis, obviously we use our x-coordinates. We say a to b of my area in terms of x. And if we're drawing cross-sections perpendicular to the y-axis, then we're using the intersection points, the y-coordinates, which in this case they call c to d of ay dy. So let's see if we can do one here for y equals 1 minus x squared over 4. So the first thing we're going to do is we need to graph this. So if we use our graphing calculator, then we can draw a quick sketch of this. So it is, what was it again? 1 minus x squared over 4. X squared divided by 4. And if I enter that, I get a parabola that's upside down, and that makes sense. And if we look at the question, it says let the base be the solid in the first quadrant, enclosed by the x-axis, the y-axis, and this graph. So if we look at that, we're just looking at this first quadrant region. So we are looking for it's going to be shifted 1 unit up, and it's going to come down like this. So there is my region. And it says when I drop slices perpendicular to the y-axis, it's forming a square. So now my slices are going from 0 to 1, so those are going to be the limits on my integrand. And now, because I'm doing the slices perpendicular to the x-axis, I have to get my equation in the form x equals. So I'm going to multiply everything by 4 to get 4y equals 4 minus x squared. I'm going to switch the x squared over here and subtract the 4y over there. And then square root, so it's going to be plus or minus 4 minus 4y. And in the first quadrant, we only take the positive branch. So there is going to be the length of that slice, which is really the length of the side length of my square. So to find the volume, it's going to be the integral from 0 to 1, and the shape again is a square, and the area of the formula for the area of a square is side length squared. Well, we found the side length right here, so it's the square root of 4 minus 4y all squared dy, And if I square a square root, we know what happens there. This is going to equal the integral from 0 to 1. The root sign just disappears, so it's going to be 4 minus 4y with respect to y. And then we just punch it in our calculator, and we get our answer. So again, the definite integral, 0 to 1 of 4 minus 4y with respect to y, and that works out to be 2. So my final answer is going to be 2. All right, let's do maybe one more here, and then we'll get into some AP questions maybe, or I think we've done enough here. Let's look at some AP questions here. And this question here is from 2007, and we'll just look at, well, we could look at all three sections, I guess. So let's do this whole question, and this might be a good place to stop, and maybe some of these other ones you guys could try on your own. But let's take a look at this guy right here. So we are, let R be the region in the first and second quadrant bound by this curve. So first thing I'm going to do, this is a calculator question, is I'm going to graph this. So first of all, I'll clear out anything I have here. And tab. And my function this time was 20 divided by 1 plus x squared. So 20 divided by, in brackets, 1 plus x all squared. And if I graph this, there's my region right there. Now, I don't see the whole graph, so I need to zoom out a little bit. And there's my graph right there. So the question is telling me I have this graph, and the first thing I want to do is I want to find the area between this graph and the line y equals 2. So I should also graph the line f of x equals 2. And I should find my two intersection points. So again, I think these work out to be whole numbers, but let's just verify that. So menu, analyze graph, we want an intersection point, left, right, and that one is -3, and then that one's going to be +3. So now I know what my limits are. My limits are -3 to +3 if I'm dealing in the x direction. Let's go back and see what the question's saying. Yes, they want us to find the area of region R. So quickly, our graph went something like this. These two intersection points were at -3 and 3. So to find the area for part A, it would be the integral from -3 to 3 of the top curve, which is 20 over 1 plus x squared, minus the bottom curve, which is 2, and I'm integrating that with respect to x. So again, to figure out that integral, we're going to go to our calculator. I'll get rid of this stuff. So I'm looking to do the integral. And again, I'm going from -3, make sure to use the negative key and not the subtraction key, to +3. I've already got my 20 over 1 plus x squared stored in function 1. So I'm just going to go f of 1 at x minus, I know my second function is stored in f2, but it's just 2, so that's not hard to enter. And I'm integrating this with respect to x. So my answer for part A looks rather ugly. However, if I convert that to a decimal, it works out to be 37.962. And now you can round off right at the end. So whoops, 37.962 is my area for part A. Now for part B, they're asking us to revolve this solid about the x-axis. So again, here's the x-axis. I'll maybe go back to my graphing calculator. If you go back to the graph, you can see that there's my region in between these two graphs. It's not touching the axes of rotation. So this is going to be a washer question. So here's my axes right here. There's my slice. I'm revolving it around the x-axis. So therefore, to find the volume, we said we're going to use the washer method. So it's going to be pi. The limits are still -3 to 3 of the outer radius squared minus the inner radius squared, all with respect to x. The outer radius is from the top of this slice down to the axis of rotation, so it's defined by the function 20 over 1 plus x squared. So it's going to be pi -3 to 3 of 20 over 1 plus x squared all squared minus the bottom of the slice is going from 2 down to the x-axis, so that's just going to be 2 squared dx. And again, now we just punch this into our calculator. And again, we can be creative here because we have that 20 over 1 plus x squared already stored in our calculator. So this is going to be the definite integral going from -3 to 3. And this is going to be the function that I have stored in F1. I should put a bracket there because I have to square it. Subtract 2 squared, which is really 4. And I'm integrating that with respect to x. And again, I get an ugly looking answer, but again, we can deal with that by converting it to a decimal. And it is 595.618. And maybe because we have the pi out front, we'll times that by pi right away because we're already rounding our answer. So times by pi, and my answer is 1871.190. So 1871.190 would be my answer to B. All right, question C now is saying the region R is the base of a solid whose cross-sections are perpendicular, cross-sections perpendicular to the x-axis are semicircles, and they want us to find the volume of this solid. So for part C, we're dealing with a semicircle. So again, my slices are going from -3 to 3, and the area of a semicircle is pi r squared over 2. Now pi over 2 is a constant, so it can come out front like before. And we're really left with the radius squared here. Now you have to be careful because this region right here is really a semicircle coming out of the screen, and that length going from the top curve to the bottom curve is the diameter. So the radius is going to be 20 over 1 plus x squared minus 2, all divided by 2. So it's very ugly, but that's what it is. So this is going to be -3 to 3 of 20 over 1 plus x squared minus 2 all over 2 all squared. Well, cleaning this up, if I square the bottom here, I get 4, and I can bring that out like I did before, and that becomes pi over 8. Squaring the top is just going to leave me with 20 over 1 plus x squared minus 2 all squared dx. So now it's a matter of entering this in your calculator. So we'll clear this out of the way. So again, we're looking for the finite integral, and I'm going from -3 to 3 of, now this was 20 over 1 plus x squared, which I already have stored in as function 1. I got to put this in brackets because I have to subtract the bottom curve, which is 2, and I have to square that whole thing because that's my radius. And if I integrate this with respect to x, that's going to be the answer for my integrand. And then I have to multiply it by pi over 8. So it's going to be pi divided by 8. And 174.268 would be the answer. So 174.268 would be the answer of the volume of my three-dimensional object, which is a semicircle. All right, so we've kind of dealt with squares, rectangles, and semicircles. The other shape that comes up the odd time is an equilateral triangle, but I'll let you look that up on your own. So basically that is the lesson for today, and the assignment is this last page, which is a handout, the last slide, sorry. So there it is right there. So you can try those, give them a whirl. The final answers are on the bottom, and if you have any questions, just send me a quick email.